statistics describing the percentiles. The median length of stay was 7 days, meaning if I took those 958 people, line them up against the wall by their length of stay, so the first person in line was the person who had the shortest length of stay. That actually was a person whose length of stay was 1 day. And at the end of the line is the person with the longest length of stay. That person actually had 49 days in the hospital. But now I look for the middle person in that lineup, the person who has about half the people in the lineup in front of him, half the people in the lineup behind him, and I ask, what's your length of stay? That person's length of stay was 7. So the median is 7 days compared to 8 days for the arithmetic mean. The reason we're getting a difference in those two numbers is this is a picture of the distribution of those 958 length of stays. What we have on the right, on the left-hand side of this picture here, these days like it used to. This is called a stem and leaf diagram. It's essentially a histogram on its side. If you took this picture and rotated it, what it would show you is that there are a few people with very, very long lengths of stay. Here's that person whose length of stay was 49. Here's another person whose length of stay was 30-some odd days. These are all different people with lengths of stays around 30. Here's a person whose length of stay was 25. But notice most of these lengths of stays are around 7 or 8 days. So when you have a distribution like this, the arithmetic mean is going to be influenced by these people with very long extreme values. Is there a way to analyze these data so that these outliers, those people with very atypical length of stay, don't have a big influence? Therefore, we want to do an analysis that doesn't rely heavily on the mean, on the arithmetic mean. Well, we'll talk about this in a few weeks when we talk about biostatistics. This is the distribution of the logarithms of those length of stays. What I took is each person's length of stay and took the natural logarithm of that number. And now calculate the arithmetic mean of those log length of stays, and the average arithmetic mean of the log length of stay was 1.93. Now, I don't know about you guys, I have a tough time interpreting what a log length of stay means. If you said that you had a patient, and I said, how long was that patient in the hospital? And you said his log length of stay was 4. I don't know how to interpret that. I'd have to take the log length of stay and somehow get rid of the log, transform it back to the original scale to figure out what a length of stay on the natural scale is to correspond to a log length of stay of 4. Now, why do we take logs? Because notice, if I looked at the median, the median length I think I hit the advance too far. Let me just look back. The median was essentially the same as the arithmetic mean. If I look at the distribution of those log length of stays, it looks almost like what you might think looks like a normal distribution in some sense. What a log transformation does is it pulls in that long tail of very long length of stays. They're still going to be bigger than everybody else's length of stay on the log scale, but they're not as spread out as far. So what the log transformation allows you to do is to give another distribution to your data, where on that particular scale, the log same values that we saw on the original scale. So on this scale, arithmetic means might make more sense. Well, finally, on that scale, there's a relationship between the arithmetic mean on the log length of stay and the geometric mean on the original length of stay scale. The relationship is that 1.93 average arithmetic mean of the log length of stays is arithmetically equal to the logarithm of the geometric mean of the original length of stay. So how you calculate geometric means in practice is instead of adding a bunch of numbers together and dividing by n, you multiply the numbers together and take the nth root. But another way of thinking about it is all you're doing is transforming your data from an original scale to a log scale, calculating then the arithmetic mean on the log scale, and taking that number, 1.93, and getting rid of the log by taking the anti-log or the exponential function of that number. And that's where the number 6.95 comes out to be the geometric mean on the original scale. So we'll talk a little bit about transformations, log transformations. But at this point in time, all I wanted to do is to just show you that when you take log transformations, essentially what you're doing is saying, I no longer want to use arithmetic means to describe my typical values on my original scale. I want to use geometric means so that they won't be influenced by these extreme values. And we'll say more about that later. Okay, so those are different outcome measures that we epidemiologists use a lot. Let me focus a little bit now on the most common outcome measures that we epidemiologists use, or binary outcomes. We epidemiologists live in a binary world. We tend to report outcomes that are either present or absent. You're either dead or you're alive. You have diabetes or you don't have diabetes. Sometimes these binary outcomes are not natural, but they're defined to be binary. So, for example, we might take blood pressure, which is measured on a continuous scale, and we might adopt a threshold saying everybody whose blood pressure is above 140 millimeters of mercury on the systolic scale, we'll call them hypertensive. Everybody else we'll call non-hypertensive. The advantage of that is we have a very familiar binary outcome. The disadvantage is we lose information. We take two people, one whose blood pressure is 141, another whose blood pressure is 139. Now we say those people are different because one person's blood pressure is above 140 and one person's below 140. And we're making a big distinction between those two people whose blood pressures are really quite similar. On the other hand, if you have two people, one whose blood pressure is 141, another one who's 161, they are greatly different. You're much more concerned about the person whose blood pressure is 161. But as far as our binary outcome is concerned, they're being treated the same. They're both being called hypertensive. If you have a binary outcome in epidemiology, the typical way we summarize them is reporting the proportion of people who have diabetes, or if we want the odds of having diabetes, and I'll talk about odds again in a second from now. So for a binary outcome, you have two choices. If I asked everybody in this room to self-declare whether they are a male or a female, we could do that just by looking at the names of the people. Let's suppose there are 40 people who are on this conference right now. Let's suppose 30 of you are women and 10 of you are men. I want to describe the gender distribution among these 40 people. There are two ways I can do it for that binary outcome gender. I can look at the proportion of people who are females. I take the 30 people who are females and compare it to the 40 people who are joining this conference. Proportion is a part over a whole. It can run from 0 up to 1, or 0% up to 100%. The alternative is I can calculate what is known as an odds. I can take the 30 people who are females and compare them to the 10 people who are males to get an idea of how common female gender is among the participants of this group. Odds run from as low as 0, when everyone in the room is a male, to infinity, where everyone in the room is a female. And one general purpose is that when you're talking about proportions which are very small, say less than 10%, the value for the odds is going to be numerically very similar to the value for a proportion. And to see that, I put this table together where I calculated or wrote down a proportion 1%, 2%, all the way up to 99%. And next to each of these proportions, I've written the odds. So if you have 1% females in the room, say 1 out of 100 people is a female, then 1 divided by 99 would be the odds. Into two decimal places, that's still 1%. We have 2 females out of 100 people. Corresponding odds are 2 divided by 98. Into 2 decimal places, that's still around 0.2. So notice when the proportions are, say, less than 5% or, say, less than 10%, the value for the odds are very similar to the value for the proportion. But if you have a room that's full of women, if I have 100 people in the room and 98 of them are women, the proportion of women in the room is 99. Corresponding odds, is 98. The